Alright, so let's take a look at an example of how to use the Gauss-Seidel method to develop a power flow solution for a power system. Now that we've defined the Gauss-Seidel method and we've taken a look at the equations for calculating the voltage at every bus and the real and reactive powers through an iteration method. And so for this example, basically, we want to solve for the power flows across this power system over here. So we have one slack bus over here on the left, we have two load buses, this one, and I've labeled them here in yellow, so buses 1, 2, and 3. And then of course we have three transmission lines that connect the three buses, and we have two loads at buses 2 and 3. And so what we want to do for this example is we want to calculate the voltage at bus 2, the voltage at bus 3, the net power at bus 1, and the power that flows from bus 1 to bus 2, from bus 2 to bus 3, bus 1 to bus 3, and the power losses in the transmission lines. So just kind of a heads up, this example is going to span over several lectures just because it's pretty lengthy to do all in one lecture. It's probably going to be 2 or 3 lectures. And so, but we're going to start solving it, and then we're going to see when we get to a good stopping point, and then we'll move to a separate lecture. But just, if you can, try to watch all the lectures back to back so that it makes a little bit more sense. Alright, so we've been given this system over here, and we're going to say that the base apparent power, which I'm going to call SB, is 100 MVA, and the base voltage, VB, is 230 kV. So this is a 230 kV system, and we're using 100 MVA as the base to convert the powers to per unit and this impedance to per unit. And I've already given the impedances over here in per unit, and of course this voltage at the slack bus is in per unit as well. And so the first thing that we need to do is we need to set up our problem. And so to do that, we need to convert first the impedances to admittances, because remember that in the Gauss-Seidel equations, everything is in terms of admittances. And then we also need to convert the powers over here, S2 and S3, to per unit. Again, because everything in our Gauss-Seidel equations are in per unit. And so that's the very first step that we need to do. So let's go ahead and do that. I'm going to say over here, I'm going to calculate the bus admittance matrix. So calculate the bus admittance matrix. And so first let's convert all impedances to admittances, and then from that we're going to calculate the bus admittance terms. And so let's do first the admittance for this transmission line. So y, lowercase y, 1, 2, it's going to be of course the reciprocal of the impedance. So 1 over z12, which is equal to 1 over 0.01 plus j 0.12. And I'm going to drop the per unit here. Everything is going to be in per unit though, that's going to be implied. But I'm going to drop the per unit word over here just to keep things a little bit more neat. So if we calculate this, we will get that the admittance y12 is equal to 0.68966 minus j 8.27586. And this of course is also equal to minus uppercase y12. Again, remember that the terms in the bus admittance matrix are these capital Y terms, and this lowercase y is just the admittance for the transmission line. And then we saw again in the bus admittance matrix lectures that the off-diagonal terms, uppercase y12 for example, is the opposite of lowercase y12. So that's where that negative sign comes from. And I'm going to try to do everything to 5 decimal places just so that we get a more accurate solution. At least for the admittances though. So next thing that we need to do is we need to calculate y13 and y23. So y13 of course is going to be 1 over z13, and y23 is going to be 1 over Z23. And again, you're going to see a lot of math in this example, but I think it's helpful to see all the solution in detail just so that you know how to use the Gauss-Seidel method yourself. And so that's why these lectures are going to take a little bit longer, but I think again that it's helpful for you to see all the details in the solution. So let's go ahead and calculate this y13. So 1 over z13, which is over here, so 0.02 plus j 0.10, and that's going to be equal to 1.92308 minus j 9.61538. And again, that's equal to minus uppercase y13. And then lastly, 1 over z23. So 1 over this impedance over here. So 0.01 plus j 0.08. And that's going to be equal to 1.53846 minus j 12.30769. That's equal to y uppercase or minus y uppercase y23. Now we know that the diagonal terms in the bus admittance matrix is equal to the summation of all the admittances that connect to a bus. So for example, the term in the admittance matrix y11 is equal to the summation of everything that connects to bus 1. So the admittance for this transmission line and the admittance for this transmission line. So that would be again y12, which is this top one over here, plus y13, which is this one over here. And then likewise for y22, we would get y12 plus y23. And for y33, we will get y13 plus y23. And so you can go ahead and plug in these numbers and these equations. So I would get for y11, that's equal to 2.61274 minus j 17.89124. And for y22 I would get 2.228 12 minus j 20.583 55. And then lastly for y33 we get 3.46 154 minus j 21.92 307. And so there we have all the terms that we're going to need in our bus admittance calculations. So y12, y13, y23, and then the diagonal terms y11, y22, and y33. And again, we're going to use this capital Y's over here. So when we use y12, we're probably going to use the opposite of this. So we're going to move the negative sign to the other side of the equation so that we get just y12. And then one last thing that we need to do is we need to also convert these powers to per unit, because again, everything in the Gauss-Seidel equation is in per unit. So S2, for example, and actually let me separate this. I'm going to say, I said over here, calculate the bus admittance matrix. Let me say over here, convert powers to per unit. Just to keep track of all the steps that we need to take for this example. So let's convert the power over here at bus 2 or rather the power for the load here at bus 2 per unit. So we know that S2 is 75 plus 15 MVA. So 75 megawatts and 50 MVA reactive. So 75 megawatts plus J 15 megavolt ampere reactive. And our base power here, we've chosen that to be 100 MVA. So we need to divide all that by 100 MVA. And again, I'm going to drop the per unit here just to keep things a little bit simpler, but this of course is going to be 0.75 plus J 0.15. Now one thing that I want to mention here as well is that for the Gauss-Seidel solution, we're going to assume that power injection into a bus is positive and power being drawn from a bus is negative. That's really important because we need to define power injection opposite to power drawn from a bus. And so for this example where we have loads at bus 2 and 3, again, these loads of course are going to draw current from that bus, meaning they're going to draw power from the bus. So we need to define in our Gauss-Seidel equation those powers as negative. So I want to say parentheses over here and negative here. So we get at the output over here minus, actually let me just go ahead and erase this. Alright, so let's go ahead and just write this again. I'm going to say minus 0.75 minus J 0.15. And then we're going to do the same thing for S3. So S3 is going to be minus, and then this power over here, so 100 megawatts plus J 10 megavolt ampere reactive. All of that over 100 MVA, which is our base. So that's of course going to be equal to minus 1.00 minus J 0.10. And I'm going to round these powers to 2 decimal places like I did over here. There's no need to be more detailed than that, of course. Alright, so we've converted everything to per unit. Everything's ready to be plugged in to our Gauss-Seidel equation. One last thing that I want to do before we move into another lecture is I want to define our assumptions for the voltages at every bus. So remember that to begin the Gauss-Seidel iterations, you need to first make an assumption for what the voltage at every bus is going to be. And that's just that, just a guess of what the voltage is going to be. It doesn't need to be correct, and it's not going to be correct. Unless, of course, just by some miracle you guess it properly. That's probably not going to be the case. So I'm going to say that V1, which V1 again is the voltage at bus 1, I'm going to say of 0. So this is iteration number 0, meaning the initial value. That's going to be equal to this voltage over here. So remember that for a slack bus, we're going to hold the voltage constant. Or rather, a slack bus, by definition, holds its voltage constant, no matter what happens in the circuit. So V1 of 0, of course, is just going to be this voltage. And that's not going to change on every iteration. So V1 of 1 and V1 of 2 and 3 and 4 and 5 and every iteration that we run is going to be the same. So I'm going to say V1 of 0 is simply just the voltage at the slack bus. So 1.03 at an angle of 0 degrees. And again, this is of course assumed in per unit, but I'm not going to use that. Everything in here is going to be in per unit. Just keep that in mind. Now just to make this a little bit simpler, of course, when we plug in this into our equations, 1.03 at an angle of 0 is just like saying 1.03. Just like we can drop this angle over here to make their equations a little bit smaller. Now V2 of 0, that's the guess of the voltage at this bus. And again, we can pick everything we want. Since this is a slack bus, or rather a load bus, we could really make an assumption that that's going to be lower than 1 per unit and with an angle lower than 0 degrees. So we could maybe guess 0.95 at an angle of -5 degrees, for example. But what I like to do personally is I just like to assume that everything's going to be at 1 per unit at 0 degrees. Because it might end up happening that it's not that much lower than 1 per unit. It would still be lower because again it's a load bus, but it could be 0.99 per unit. And so that's fairly close to 1, which means that if I guess 1 initially, I'm going to have to perform less iterations to get to the actual solution. And so since I don't really know what that voltage is going to be, I'm just going to assume 1 per unit at an angle of 0 degrees. So I'm going to say V2 of 0 is going to be 1.00 at an angle of 0.00. Or actually for this, let me do 3 decimal places. So let me erase this. Let's go back 1.000 at an angle of 0.000 degrees. And same thing for bus 3. So V3 of 0 is going to be 1.000 at an angle of 0.000 degrees. And here I'm not going to drop the angle because again, once we run our iteration, we're going to see that that angle and this magnitude are going to start to change. So I'm not going to drop the 0 degrees like I did here for bus 1. Alright, so we have our problem set up now. Now we can move into performing the iterations of the Gauss-Seidel method. But I think this is a good stopping point. Let's go ahead and stop here. We've defined our bus admittance matrix. So these are the terms that we're going to plug into our Gauss-Seidel equation. We've defined, or rather converted, the powers per unit, and we've defined our initial guesses for the voltages. So I think this is a good stopping point. Let's move into the next lecture where we're actually going to start performing iterations of the Gauss-Seidel method. Alright, so I've gone ahead and grouped everything that we're going to need for our equations over here on the bottom left. And I made it a little bit smaller just so that I could make room over here to perform the iterations. So, but it's over here just for reference. And then again, here's our system that we're going to be using for this example. And so let's go ahead and run the first iteration then. Of course, we know that the voltage at bus 1, again, since that's a slack bus, that's going to be fixed at 1.03 per unit. So what we need to do for this example is we need to calculate the buses, or rather the voltages at the buses 2 and 3, which are load buses. Since we know the real power and the reactive power at every bus, but we don't know what the voltage is. And so in every iteration, basically what we're going to do is we're going to calculate the bus voltage, again using this initial guesses to 1 per unit at 0 degrees. Then we're going to calculate the voltage at that bus. We're going to get a different value. We're going to see that that's of course different than our guess. We would put that back into the equation and run a second iteration, and then we're going to do that a couple times until we get a solution that converges to a certain value. So let's go ahead and do that. I'm going to say over here, I'm going to run the first iteration. And of course, like I said before, there's going to be a lot of math and a lot of just algebra here in this example. But again, I think it's helpful to see the whole solution for you to understand how this method works. And so using the Gauss-Seidel equation that we derived before, I can say then that the voltage at bus 2 for the first iteration, so I'm going to call that V2 1. So again, this right here resembles, or not resembles, this right here means that this is the iteration number 1. So iteration 0 was just our initial guess. Then iteration 1, I would put 1 over here, and then 2, I would put 2 over here, 3, 4, and 5. But I just want to point out that that's not V2 to the 1. That's V2 iteration 1. This is not an exponent. So using the Gauss-Seidel equation, I can calculate the first iteration as the following. So I'll get that V2 of 1 is going to be equal to P2 minus J Q2, these being the powers at bus 2. So P2 is the real power at bus 2 and Q2 is the reactive power at bus 2. That over V2 conjugate of the previous iteration, so of iteration number 0. And then that minus uppercase Y12 times V1 of 0 minus Y13 V3 of 0. And again, here I'm going to use the latest information that I have. So for V1, the latest information that I have is iteration 0. And for V3, the latest iteration, or rather the latest information that I have is iteration 0 as well. So all of that divided by Y33. And so now we can go ahead and plug in the numbers. So I can say then P2 is going to be over here, so minus 0.75. And notice here that I have P2 minus JQ2, not plus JQ2. So P2 is minus 0.75, but minus Q2 is going to be the opposite of this. So I'm going to get over here then minus 0.75, but then plus J 0.15. Again from here I got 0.75 from here, but then I take minus Q2, but Q2 is minus 0.15, so that would be positive 0.15. And then that over the conjugate of V2 for the previous one, or rather for the previous iteration. So V2 of 0 is 1 at an angle of 0, so the conjugate of that is going to be the same thing. So 1 at an angle of 0. And then minus Y12, which I have over here. So Y12, or rather minus Y12 is equal to this whole thing. So I need to take the opposite of this. So minus, and then minus 0.68966 plus J 8.27586 times V1 of 0, which is just 1.03. And then minus Y13, which again, Y13 is the opposite of this. So minus 1.92308 plus J 9.61538. And I'm running out of room over here. That times V3, which is just 1. Or 1 at an angle of 0, which is just 1. So all of that divided by Y33, which is over here. So all of that divided by 3.46154 minus J 21.92307. So you can see how easy it would be to make a mistake over here. So you have to be very, very careful when you're plugging in numbers, making sure your signs are correct and making sure that you're plugging in the right number for the right thing. It's very easy to make a mistake over here. And it's also very easy to make a mistake when you're plugging all this into your calculator. And so what I do is typically I just write everything down, double check everything, calculate it with my calculator, get a number, write it down, calculate it again, just double check everything, because again it's really easy to make a mistake over here. And so, but if I calculate this, I would get the V21 is going to be equal to 1.00093 minus J 0.03553. And again, I'm going to use 3 decimal places over here, and just so that we can compare it to this number over here in polar form, that's equal to 1.00156 at an angle of minus 2.03297. That's V2, again, V2 iteration 1. And so you see here how we start getting a different value than our initial guess. So I already know that my initial guess, of course, as I assumed it was wrong. So I run my first iteration, I get this number. Now when I run the second iteration, I'm going to use this number in here. Instead of V2 of 0, this is going to become V2 of 1, and this is going to become V2 of 2. And so I will get a different number for a second iteration. And again, we're going to continue to do this until we get a solution that converges. Alright, so let's keep going. Let's do now V3 of 1. And I notice that this space here is kind of small, so I'm going to try to write a little bit smaller so that I don't run out of room here on the right. So, but V3 of 1 is going to be given by the following equation. So P3 minus JQ3 over V3 conjugate of 0. So again, the previous iteration minus Y13 V1 of 0 minus Y23 V2, and again, this is what I mentioned before, you have to use the latest information that you have. So notice that in the V2 equation I use V3 of 0. So here I'm not going to use V2 of 0 because I already know what V2 of 1 is. So I have to use my latest information available in this solution over here. That's going to help speed things up because again, I know that this solution wasn't right because I got this solution now for iteration 1, so let's go ahead and use that in our equation over here. So always use the latest information that you have for performing your iterations. So all of that divided by Y33. So V3 of 1, and again I'm going to try to fit everything over here. So that's going to be this power over here, S3, so minus 1.00, and again the reactive power would be opposite to this, so plus J 0.10 over V3 of 0 conjugate, so this number, of course 1 and an angle of 0, conjugate of that is just 1. So 1 and an angle of 0, then minus Y13, which is over here. So minus 1.92308 plus J 9.61538 times 1.03, then that minus Y23. So Y23 is over here, so minus 1.538 46 plus J 12.30769 times V2 of 1, which is this number over here. So times, and I actually did run out of room, so let me write it down over here, times 1.00093 minus J 0.03553, and then all of that divided by Y33, which is over here. So all of that divided by 3.46154 minus J 21.92307. And actually notice over here that I wrote down Y33. This should have been Y22 because again, this is the calculation for voltage 2. So let me go ahead and erase that. So again, this should have been Y22, which means that the number over here should have been this number over here. So 2.22812 minus J 20.58355. Now this number is correct because I already calculated that in my notes. So even though I wrote down here Y22 and here, or rather Y33 and here Y33, I wrote down this number from my notes in which I did use Y22. So this number is correct. I just wrote down over here Y33 instead of Y22. But this solution again is correct. And so now if we solve for V31 over here, let me put it over here on the left, V31 is going to be 1.00165 minus J 0.06312. And again, just so that we can compare to our initial guess, let me write that down in polar form as well. That's equal to 1.00363 at an angle of minus 3.60601. Alright, so you see how this is starting to get very, very complex, and we only have run one iteration so far. We're actually going to do 3 iterations for this example, just so that we can start seeing how our solution is going to start to converge to a certain value. So I think this is a good starting point. Let's do 1 iteration per lecture. So let's go ahead and move to the next lecture. We're going to do 1 more iteration, then we'll move to the next one, do 1 more iteration, then we're going to have a final lecture where we're going to kind of summarize everything. Alright, so we left off over here after the first iteration of our Gauss-Seidel solution to this power flow, or rather for the power flow for this power system over here, where we got that V2 of 1 was this number over here and V3 of 1 was this number over here. So let's go ahead and run the second iteration. So I'm going to say over here second iteration, and this is going to be of course similar to the first iteration. So I'm going to say then that V2 of 2 is going to be equal to P2 minus J Q2 over V2 conjugate, but now of the first iteration, so the previous iteration, and then minus uppercase Y12 V1 of 0. Again, V1 is the voltage at the slack bus, so that's not going to change, so I can always use the initial voltage because that's going to be the same as the iteration 1, 2, 3, 4, and 5. That's going to remain constant. And then minus Y23 V3 of 1. And then all of this over Y22. So now let's go ahead and plug in the numbers. We know what the powers are, so that's going to be minus 0.75 plus J 0.15. And I'm trying to write it a little bit small here just so that I don't run out of room here on the right. But all of this over now the conjugate of this number over here. So that's going to be 1.00156. And then I have over here minus 2.03297. So the conjugate of that is going to be positive 2.03297 degrees. And I'm going to write these voltages in polar form just to save a little bit of room. And so now minus Y12. So minus 0.68966 plus J 8.27586 times the voltage at bus 1, which is just 1.03, again that being the slack bus, that's going to remain constant, and then minus Y23, which is over here. So the opposite of that would be minus 1.53846 plus J 12.30769. And it looks like I'm going to still run out of room. It's kind of hard to fit all of this into one line. So, but I will get this times V3 of 1. So let me put it underneath it. So V3 of 1 is this number that we got over here. So 1.00363 at an angle of minus 3.60601 degrees. And then all of this over Y22, which is this number over here. So 2.22812 minus J 20.58355. And again, I know that this is a lot of numbers over here, but I'm just trying to show you the whole process for calculating these iterations. And so if I calculate this, I would get that V22 is going to be equal to, in rectangular form, 1.0 0.00132 minus J 0.07286. And let's also calculate that, or rather convert that to polar form, just so we can compare it to this number over here. So we get that that's equal to 1.00397 at an angle of minus 4.16173 degrees. This again is V22. And so you see that it's starting to go up in magnitude, but the angle is going down. So the angle over here was minus 2 degrees, and the angle over here is minus 4 degrees. And notice the difference between the two numbers. So in magnitude, this is 1.001, and this is 1.004 almost. So this solution isn't converging yet. We need to run more iterations to get an accurate solution. And so, but let's also do the same thing for V3 of 2 then. So the second iteration for V3. So that's going to be P3 minus JQ3 over V3 conjugate of 1 minus Y13 V1 of 0 minus Y23 V2. And again, I'm going to use the latest information that I have for V2, which is this one over here that we just calculated. So V2 of 2, all of this divided by Y33. And so let's go ahead and plug in the numbers. We would get minus 1. And actually, let me try to write this down a little bit further to the left. So we get minus 1.00 plus J 0.10 divided by the conjugate of this number over here. So V3 of 1 conjugate. So 1.00363. But then I have to take the conjugate here. So instead of minus 3.6, I'm going to do positive 3.606. 0.1 degrees. And then minus Y13, so that's minus, parentheses, minus 1.92308 plus J 9.61538 times V1, and again V1 remains constant, so that's just going to be 1.03, and then minus 1.53846. I missed the minus over here, so minus 1.53846 plus J 12.30769. And then that times V2 of 2, which we calculated over here. So 1.00397 at an angle of minus 4.16173 degrees. All of this divided by Y33. So Y33 is over here, so 3.46 154 minus J 21.92307. And so if I calculate all this, let me just put it over here. V3 of 2 is going to be in rectangular form 0.99851 minus J 0.08302. 0.8302. And again, let's write that down in polar form just so that we can compare it to this number over here. So that's going to be 1.00195 at an angle of minus 4.75 271 degrees. And so again, let's compare that to this number over here. I got over here 1.00363, and here I have 1.00195. So I see that this is coming down. But then also, just like for V2, the angle is also coming down. So for here I got minus 3.6, and here I got minus 4.8 if we round to one decimal place. So I see that the angles are coming down. The magnitudes seem to be staying pretty constant. This one went down a little bit, and this one actually went up a little bit. So we have to keep running iterations again until we see that our solution converges. And for this example, we're probably going to have 5 or 7 iterations before we get to a solution that we know has converged. But we're just going to run one more iteration. So we're going to do 3 iterations in total, and you know what the process is, so you can do more iterations if you want until your solution converges, which I did in my notes, and I'm going to put down in the next lecture what the actual solution is. So in the next lecture, we're going to run one more iteration, and in the lecture after that, we're going to see all the 3 solutions that we got for the 3 iterations and compare them to each other. And I'm also going to write down what the actual solution is after you run several iterations, probably in the 7 iteration range. Alright, so let's run the 3rd and last iteration that we're going to be running for this example. So of course by now we know how to write these equations for the Gauss-Seidel method. I'm going to say that V2 of 3, so the voltage at bus 2 3rd iteration, is going to be equal to P2 minus J Q2 over the conjugate of V2 for the previous iteration, so V2 of 2 minus Y12 V1 of 0, and again, if this wasn't a slack bus, I would use V1 of the last iteration, minus Y23 V3 of 2, so the last iteration for V3, all of that divided by Y22. So let's go ahead and plug in the numbers. We would get that this is equal to minus 0.75 plus J 0.15 over the conjugate of V22. So we calculated V22 over here. It's this number over here, so 1.00397, and I take the conjugate of that. So instead of minus 4.16173, I would do positive 4.16. So 4.16173 minus Y12, so minus 0.68966 plus J8 point 27586 times the slack bus, so 1.03 minus Y23, so minus 1.538 46 plus J12 307.69. And then all of that times V3 of 2. So V3 of 2 is over here. And let me see if I can fit it in over here. It's 1.00195. And I think I'm going to run out of the room. So let me put the angle over here. Minus 4.75271. So all of that divided again by Y22. So all of this divided by Y22, which is over here, 2.228, 12 minus J, 20.583, 55. Alright, so this is a pretty lengthy equation again. If we calculate all of this, we would get that V22, or rather V23, is going to be equal to, in rectangular form, 0.99838 minus J 0.08424. And again, let's write this down in polar form as well, just so we can compare it to the previous result. This is 1.00193 at an angle of minus 4.823. 82300. So this is again V2 iteration number 3. And so comparing that to V22, we see that the magnitude went down now. Remember that from iteration 1 to 2 it went up, and also from 0 to 1 it went up as well. So 0 was of course 1, which was our initial assumption, and then V2 of 1 went up in magnitude a little bit, V2 of 2 went up in magnitude again, but now it's starting to come down. And notice that the angle now didn't change that much. So between iterations 0 and 1 it went up by, or rather down by minus 2 degrees, and then it went down again by another minus 2 degrees, but now it's starting to level off. So from iteration 2 to 3 it only changed by, looks like 0.7 degrees. So the angle is starting to converge. We see that the magnitude is starting to go down, which is what we expected for a load bus. Again, for a load bus we would expect the magnitude to be lower than the slack bus. And so we see that that's starting to happen. The magnitude is starting to go down, and again the angle is starting to converge. It only changed 0.7 degrees from iterations 2 to 3. So it looks like it will settle somewhere in the minus 5 degrees range. But let's go ahead and do iteration 3 for V3 as well. So V3 of 3 would be equal to P3 minus JQ3 over V3 conjugate of the previous iteration, so V3 of 2 minus Y13 V1 of 0 minus Y23 V2, and again we used the last iteration or the last information that we have, which for V2 is this third iteration. And so all of that divided by Y33, and I'm going to put it over here on the right just to save some room over here. And so now if we calculate all this, we would get minus 1.00 plus J 0.10 over V3 of 2 is over here, so 1.00195 at an angle of the conjugate of this, so 4.75 positive 271, and then that minus 1.92308 plus J 9.61538. And of course for this I'm looking at my notes that I already solved all of this, but all of that times 1.03 minus 1.53846 53846 plus J 12.30769. All of that times V2 of 3, so this number over here. So 1.00193 at an angle of minus 4.82300 degrees. And then of course all of this divided by Y33. So all of this by, or rather divided by this number over here. So 3.46154 minus J 21.92307 307. And again I ran out of room again over here, so let me put the result over here. I'm going to say V3 of 3 is going to be equal to this number. So in rectangular form, 0.99578 99578 plus J, or rather minus J 0.08910. And that in polar form is 0.99976 and an angle of minus 5.11307. And so let's compare this to the previous result. We see again that the magnitude also went down for V3. Now it's starting to come below 1 per unit. And again, you see that the angle from the first iteration to from the initial guess to the first iteration changed by 3 degrees, looks like, or minus 3 degrees. So it went from 0 to minus 3.6 over here. Then from that to the second iteration, it changed by more than 1 degree. So looks like minus 1.1 degree. But now from iteration 2 to 3, so this number over here to this number over here, it only changed by, looks like, minus 0.4 degrees. So again, we see that the angle is starting to converge, and we see also that the magnitude changed slightly. It went down, just like the voltage for bus 2 also went down. And so we're starting to see a trend over here. The magnitudes are starting to go down. They will eventually go down also for voltage at the bus 2 below 1 per unit. And we see that the angles are starting to settle somewhere in the minus 5 degree range. Alright, so that's the third iteration. In the next lecture, we're going to summarize all the voltages, and we're also going to see what the actual result after we run several iterations is. Alright, so we've gone ahead and done 3 iterations for the power system in this example. And I just want to go over the results that we got just to kind of summarize everything in this lecture. So of course we assumed initially that the voltage at buses 2 and 3, so these 2 buses over here, was 1 per unit. So for iteration 0, meaning the initial guess, again 1 per unit for both voltages. Then for iteration 1, we saw that the angles starting to come down. So we got for V2, we got minus 2.03. For V3, we got minus 3.6. But the magnitudes went up a little bit. So they went in the opposite direction of what we would expect for a load bus. Remember that for a load bus, we were expecting the voltage to be lower than the slack bus. But notice though that the slack bus is at 1.03 per unit. So these aren't really higher than the slack bus that we were expecting, but I was expecting the voltage to be a little bit lower than 1 per unit as well. So lower than the slack bus and lower than 1 per unit. That's not always true though. It could be that the voltages are below the slack bus. That's almost always true. So in this example where the slack bus is at 1.03 per unit, voltages at bus 2 and 3 could be at 1.01 and 1.02 per unit, and they would still meet that criteria. However, they went up from our initial guess. Then for iteration 2, we saw that they went up again. So the voltage went up from 1.001 per unit to 1.003 per unit, roughly 1.004 per unit. But notice that the angles went down for both as well. So for bus 2, it went down from minus 2 degrees to minus 4 degrees, and for bus 3, it went down from minus 3.6 to minus 4.8 degrees. Then for iteration 3, we saw that the angles again went down a little bit, but not by much. So we started to see a convergence here in the angle between iterations 2 and 3. So for bus 2, we got minus 4.16 for iteration 2 and minus 4.82 for iteration 3. So not that big of a change. And then same thing for bus 3. We saw that the angle for iteration 2 was minus 4.75 degrees, but for iteration 3 it was minus 5.11. So roughly a 0.4 degree change. So again, it didn't change by much. Now if you keep running these iterations, you would eventually converge to a value, and I went ahead and simulated this power system in MATLAB Simulink just to see what the value would actually converge to. And so this number right here at the bottom is the actual voltage that we would see if we keep running iterations, probably in the range of 5 to 7 iterations for this example. And so we see that the angles were not that far off even at iteration 3. So for the voltage at bus 2, it was only 0.3 degrees off, and for the voltage at bus 3, it was less than 0.2 degrees off. So this was again starting to converge, especially the angles were pretty close to the actual result. And the magnitudes as well. See that the voltage for bus 3 that we got in iteration 3 was 0.99976, and the final result would have been 0.997. So 0.002 per unit off from our result. But you should know by now how to run the iterations, so you can continue to do the iterations until you see a value that converges. In other words, you would compare the real part and the imaginary part of the voltage at every bus and compare 2 consecutive iterations, and then once that value, or rather once those values are below a certain threshold, which you could call maybe epsilon, would be somewhere in the 0.0001 per unit range. So once you see a change that's smaller than that, then you can say that your solution converged. Now, one last thing that I want to do for this example, and we're probably going to have one more lecture before we wrap up this example, is we want to calculate the power flows through the transmission lines in the system, as well as the power losses in the transmission lines. And so to do that, we need to calculate the current in the system. But now that we have the voltages at every bus, then that's pretty easy to do. So first thing that I want to do is I want to calculate the net power that's being inputted by this slack bus over here. And so to do that, I can use the following equation. I can say that P1 minus JQ1 is going to be equal to V1 conjugate times V1 Y11 plus V2 Y12 plus V3 Y13. And again, this is an equation that we derived before. And so plugging in the numbers over here, I would get that this is equal to 1.03. Of course, the conjugate of 1.03 at 0 degrees is the same thing. And then that times 1.03 times Y11, which from the previous example, that was equal to 2.61274 minus J 17.891 24, and then all of that plus V2. So V2 actual, I'm going to use this one over here. So 0.9986, 0.9986 at an angle of minus 5.15 degrees. That times Y12, which is equal to minus 0.68966 plus J 8.275 86. Then that plus V3, which is 0.9973 at an angle of minus 5.3 times Y13, which is minus 1.92 308 plus J 9.61583, or rather 61538. And so if I calculate this, I would get that the power, again, the power inputted by this slack bus over here in per unit is 1.77482 minus J 0.42196. Again, this is in per unit. And so converting this to megawatts and megavolt amperes, remember that our base in this example is 100 MVA. So we get that the power is 177.48 megawatts, the real power rather, and the reactive power is 42.20 megavolt ampere reactive. So that in this diagram would be, again, the power that's inputted by this generator. So I can say over here I get 177.48 megawatts, and I get also the reactive power 42.20 megavolt ampere reactive. So that's the input to this bus by the slack bus. So in the next lecture, which is going to be the final lecture, we're going to calculate the power flows through the transmission lines, and we're going to calculate the power loss in every transmission line. Alright, so this should be the last lecture for this Gauss-Seidel example. And as you see, we've had 6 parts of this example just to solve one power system with 3 buses and 3 transmission lines. So, but the last thing that I want to do is I want to calculate the power that flows through each transmission line and the power losses in every transmission line. And so to do that, first thing we need to do is we need to calculate the currents that flow through each transmission line. And then from that we can calculate the sending end power, the receiving end power, and the power loss in every transmission line. And so now that we know the voltages at every bus, calculating the current is fairly straightforward. So the first current that I'm going to calculate is I12. I12 is the current that flows from bus 1 to bus 2. So in this direction, and it's defined as going from bus 1 to bus 2, not the other way around. And so I can say then that that's also equal to minus I21. In this case, I21 would be the current that flows from bus 2 to bus 1. And so of course the current that flows from bus 1 to bus 2 is opposite to the current that flows from bus 2 to bus 1. This is just a matter of notation so that we can use this when we calculate the sending and the receiving end powers. And so but basically I12 is going to be equal to the admittance Y12 times the difference in voltages between bus 1 and bus 2. So V1 minus V2. And so this would be equal to, and I went ahead and wrote down the admittances just for reference here in this red box over here. And so Y12 is equal to 0.68966 minus J 8.27586. And so that times V1 minus V2. And so V1 is of course the slack bus, so 1.03 minus V2, which is equal to 0.9986 at an angle of minus 5.15 degrees. So if I calculate this, I get that I12 is equal to 0.80044 at an angle of minus 16.80378 degrees. And so we can do the same thing for I13, which of course is going to be equal to minus I31, which is equal then to Y13 times V1 minus V3. So Y13 is over here 1.92308 minus J 9.61538. That times V1, so 1.03 minus V3, so minus 0.9973 at an angle of minus 5.30 degrees. And so if we calculate this, we get that that current is equal to 0.97333 at an angle of minus 10.55324 degrees. And then lastly, let's calculate the current that flows from bus 2 to bus 3. So I23, which again is going to be equal to minus I32, and that's going to be equal to Y23 times V2 minus V3. And so Y23 is over here 1.53846 minus J 12.30769. All of that times V2, which is over here 0.9986 at an angle of minus 5.15, minus V3, which is over here, so 0.9973 at an angle of minus 5.30 degrees. And so if we calculate that, we get that current is equal to 0.06, or rather 0.03620 at an angle of minus 24.55415 degrees. And of course, all these currents are in per unit. So this is per unit, and per unit. And so now at every bus, we can calculate the powers at every bus. So let's go ahead and do that over here on the top. I'm going to define the power S12 as descending end power from bus 1 to bus 2. So in other words, the power that flows through this transmission line out of bus 1. Now we're going to have a loss in the transmission line. So the power that comes out of bus 1 is not entirely going to flow into the bus 2. We're going to have a drop, or not a drop, but a loss in this transmission line. And so S12 is going to be equal to V1 times I12 conjugate. And if I calculate that, I get that that's equal to 0.7892 minus J 0.2383. And so here I'm not going to go over the entire calculation, but V1 is over here, so 1.03, and I12 we just calculated, so it's over here. And so you can just take those two numbers, multiply them together. Of course, you got to take the conjugate of I12, and you would get this number. Now this is again in per unit. Now S21 is going to be equal to the voltage at bus 2 times the current I21 conjugate. And so this is why I mentioned that it's important that we define I12 and I21. So we got I21, or rather minus I21 is equal to this. So you have to take the opposite of that and then multiply times V2 to get S21. And so if you calculate that, you will get that S21 is going to be equal to minus 0.7828 minus J 0.1615. And actually just notice over here this should have been a plus sign. So we can do the same thing for S13 and S31. So let's go ahead and do that. S13 is going to be equal to V1 times I13 conjugate, and S31 is going to be equal to V3 times I31 conjugate. So if we calculate that, we would get that S13 is equal to 0.9856 plus J 0.1856, or rather 1836, and S31 is equal to minus 0.9666 minus J 0.0889. And then lastly, we can calculate again S23 and S32. So S23 would be equal to V2 times I23 conjugate, and S32 would be equal to V3 times I32 conjugate. And so we would get for S23 that that's equal to 0.0341 plus J 0.012, and S32 would be equal to minus 0.0341 as well, and minus J 0.0190. So again, all of these are in per unit, and remember that our base, or rather our power base, is 100 MVA. So to convert all these per units to actual megawatts and megavolt ampere reactives, we will just have to multiply times 100 MVA. So let's go ahead and draw that here on the power system. So this is what we're going to call the power flow diagram, meaning we're going to draw the power flows through the entire power system. And so we see that S12 has positive on both the real and the reactive parts. So we can say then that I'm going to put real power on the top and reactive power on the bottom. So out of bus 1 to bus 2, we see a flow of 78.92 megawatts. Again, remember that I'm multiplying this times 100 MVA to convert from per unit to megawatts and megavolt ampere reactive. So we would get 78.92 megawatts flowing this way. And we would get also 23.83 megavolt ampere reactive. And so notice, of course, that S21 also matches that. So we see that we have negative over here and negative over here. So we know that we have power coming into the bus. And so that would be 78.28 megawatts and 16.15 megavolt ampere reactive. So M var. Now S13 is over here, again positive in both the real part and the reactive part. So from bus 1 to bus 3 we would get a flow this way of 98.56 megawatts and 18.36 megavolt ampere reactive. And then receiving on the bus 3 end, so S31, we see again negative and negative. So that confirms that we're receiving that power. And we get 96.66 megawatts. I'm going to try to write it over here on the left. So 96.66 megawatts and 8.89 megavolt ampere reactive. So 8.89 MVARs. And then lastly, from bus 2 to bus 3, we see that we have a flow from bus 2 to bus 3. Again, because we see here S23 has positive on both the real and the reactive part over here. So the flow is this way. And we get 3.41 megawatts and 1.2 megavolt ampere reactive. And then on the receiving end, we get 3.41 megawatts and 1.9 megavolt ampere reactive. Now again, notice, for example, here on the transmission line that goes from bus 1 to bus 2, that we're sending 78.92 megawatts, but we're only receiving 78.28 megawatts. And so the difference between those two numbers is the loss in the transmission line. Because of course we have a resistance in the transmission line and we have an inductance in the transmission line as well. So we're going to have both a loss of real power and we're going to have a consumption of reactive power as well.
Automation.
So a common notation that you might see in power flow diagrams is to say here in parentheses, we're going to write down the losses. So we get a loss of basically this number minus this number, so 0.64 megawatts and 7.68. We're only receiving 78.28 megawatts and 3.41 megawatts and 1.9 megavolt ampere reactive. Now again, notice, for example, here on the transmission line that goes from bus 1 to bus 2, that we're sending 78.92 megawatts, but we're only receiving 78.28 megawatts. And so the difference between those two numbers is the loss in the transmission line. Because of course we have a resistance in the transmission line and we have an inductance in the transmission line as well. So we're going to have both a loss of real power and we're going to have a consumption of reactive power as well. So a common notation that you might see in power flow diagrams is to say here in parentheses, we're going to write down the losses. So we get a loss of basically this number minus this number, so 0.64 megawatts and 7.68 megavolt ampere reactive. And then on transmission line 1-3, we have a loss of 1.90 megawatts and 9.47 MVARs. And then lastly, on the transmission line 2 to 3, we have a loss of, basically these two numbers are equal to each other, so 3.41 and 3.41 megawatts. Now there's obviously going to be a loss in this transmission line, but I think just because of rounding errors, or rather we've approximated everything to 2 decimal places on a megawatt level. And so that's why it seems like there's no loss in there, but there's actually going to be a loss. It's just that when we round to 2 decimal places on a megawatt level, we don't see that loss. And so I'm going to put it here 0.00 megawatts, but just know that there actually will be a loss in the transmission line. We just lost that accuracy when we're rounding to 2 decimal places, and especially on a megawatt level. So if you think about 0.01 megawatts is 10 kilowatts, so that's a significant amount of power. And then we also lose 0.01 megavolt ampere reactive. And so just a couple checks here that you can make just to make sure that your calculations are correct. If you notice here, we're injecting 177.48 megawatts into this bus. And we see that we have 78 flowing through this transmission line and 98 flowing through this transmission line. So these two numbers added up should add up to this number. And we see that that's the case. So we have 98 point something and 78 point something, so that's roughly 177 megawatts. Same thing for the reactive power. So we see here 23 mVars and here 18 mVars. So if you add up 23 plus 18, that's 41 mVars, and then we have some decimals here, so that's roughly 42 mVars that we get over here. And so you can do checks like that just to make sure that your numbers came out right. Another check that you can make is that you know how much power you're putting into the system. For example, I have 177 megawatts. That's the only source in the system. I know that this load is drawing 75 megawatts. I know that this load is drawing 100 megawatts. So those two added up is 175. And then I have a loss over here of 0.64 megawatts and a loss over here of 1.9. So all those numbers added up adds up to this 177 megawatts. In other words, whatever we're injecting into the system, in this case, this being the only source in the system, needs to add up to all the loads in the system plus the losses in the transmission lines. So you can do a check over here, and I already went and did that, and everything checks out. So whatever I'm putting in on real power adds up to the real power in the loads plus the losses in the transmission line. Same thing for the reactive power. The reactive power that we put into the bus 1 adds up to the reactive power of the loads plus the reactive power that's consumed by the transmission lines in the system. Alright, so that's the entire example. We basically took almost about an hour to solve this system from scratch. So basically we started with a guess for bus 2 and bus 3, or rather the voltages at bus 2 and bus 3. We calculated that doing several iterations until our solution converged. Or actually we only ran 3 iterations, and then we used the simulation to get the actual number, which it probably would have taken us 5 to 7 iterations to get to that number. And then from that we calculated the currents that flow in each transmission line, and then from that we calculated the powers that flow through each transmission line and the power loss in every transmission line. So you can see how these power flow analyses are very complex, and if you do them by hand it would take forever to perform. This example, for example, took us about an hour to solve, and it's a fairly simple system. I mean, we only have 3 buses and 3 transmission lines and 1 slack bus. We didn't even have another generator in the system. And so this can get very, very complex very quickly, and it becomes really inefficient to do by hand. But now that you know how the power flow equations work and you know how to set them up, you know how computer programs that perform power flow analysis work. So basically they're doing these calculations in a program to do the iterations quicker using a computer, obviously. And so by knowing this theory behind how power flow works, you can go ahead and set up your own power flow program that would perform these calculations automatically. And so that's the importance of knowing the theory behind these methods for calculating power flow. That way you know what a computer program is doing to perform a power flow for a large system. But it's not practical to solve a power flow, or rather to perform a power flow analysis by hand for large systems.